We live in a world full of claims about health of the universe, food technology, and everything in between. Some are true, some are half true, some are just wrong. So, how do we figure out which ones we should trust? That's where the scientific method comes in. It's not a belief system or a set of facts. It's a simple, powerful way of thinking that helps us test ideas, challenge assumptions, and discover what's actually real. Today, we're going to break it down in the plainest way possible, using stories and logic anyone can follow. Once you understand this method, the world starts making a lot more sense. How do we actually know what's true about the world? It sounds like a simple question, but it's one of the most important questions humans have ever asked. Because without a reliable way to separate truth from error, we couldn't build medicine technology, engineering, or even basic knowledge. We would still be guessing about everything. And the method that allows us to know what's real is not a set of facts. It's not a textbook. It's a process, the scientific method. A simple but powerful way of thinking that anyone can use to understand reality more clearly. Today, we're going to break down this method in the simplest way possible. No jargon, no complicated terminology. Just a clear, logical story of how we figure out what's true. And by the end, you'll see that science isn't something distant or elitist. It's something you already use every day, and something you can use even better once you understand it. Let's begin with the big idea. Science is not a belief. Science is a tool, a way of checking which ideas match reality. People sometimes say, "I believe in science," but that phrase misses the point. Science is not something you believe in. It's something you use. It's a method anyone can apply. Children, students, researchers, even people doing everyday tasks like cooking or fixing a problem at home. At its core, the scientific method follows a simple loop: observe. Ask a question, form a hypothesis, test it, analyze the results. And if the results don't match your hypothesis, change it. That's it. But this simple loop has unlocked everything from the laws of motion to vaccines to electricity to understanding the age of the universe. Let's go step by step, starting with the first part: observation. Observation is where curiosity begins. You notice something interesting in the world. Maybe you see an apple fall from a tree. Maybe you watch two objects drop at different speeds. Maybe you see that food spoils faster in summer than in winter. Observations spark questions. And that leads to the second step: asking a question. Why does this happen? What's causing it? Does this always happen or only sometimes? A good scientific question is specific and testable. Instead of asking, "Why is everything the way it is?" you ask, "Why do objects fall downward?" Or "Do heavier objects fall faster than lighter ones?" Or "What makes bread rise?" These simple questions can unlock entire fields of knowledge. After the question comes, the hypothesis, a prediction or explanation you can test. A hypothesis doesn't have to be correct. In fact, many of history's greatest hypotheses were wrong at first. The important thing is that a hypothesis makes a clear prediction. For example, heavier objects fall faster than lighter ones. Or heat causes bread to rise. Or germs cause disease. The hypothesis gives you something concrete to test. And that brings us to the fourth step: experimentation. Experiments are the heart of science. They allow us to check whether our predictions match reality. The key is that experiments must be designed so the results are clear, repeatable, and unbiased. Let's take a simple example. Imagine you want to test whether heavier objects fall faster. You take two objects of different weights, drop them from the same height, and watch what happens. Galileo supposedly did a version of this centuries ago and discovered that weight didn't matter. Objects fell at the same speed in a vacuum. Or consider germs. Before the 1800s, many people believed diseases came from bad air. But Louis Pasteur designed experiments that showed something entirely different. By sterilizing equipment and exposing it only to air that filtered out microbes, he demonstrated that microorganisms were responsible for disease. That experiment helped build modern medicine. Experiments test ideas against reality. If the idea doesn't match the results, we adjust or reject the idea. And that leads to the fifth step, analyzing and concluding. If your hypothesis was wrong, you change it. If it was right, you repeat the experiment or let others test it. Science never says this is the final answer forever. Science says this is the best explanation we have right now, and we will update it if new evidence appears. That willingness to change is not a weakness. It is science's greatest strength. Because the world is complex. New tools reveal new details. New experiments uncover new patterns. And science constantly sharpens its understanding. But to fully understand the power of the scientific method, we need to talk about two concepts. People often confuse hypothesis and theory. A hypothesis is an early guess, a starting point. A scientific theory is a powerful, well-tested model that explains a large set of evidence. A theory is not a vague idea. Gravity is a theory. Evolution is a theory. Germ theory explains why infections happen. These theories have been tested thousands of times and have never been contradicted by experiments. They're our best explanations of how reality works. The word theory in everyday conversation means a guess. But in science, it means a model supported by mountains of evidence. Now, let's talk about something else essential to science reproducibility. If only one scientist gets a certain result, that isn't enough. Maybe they made a mistake. Maybe their equipment was faulty. Maybe they got lucky or unlucky. But if many scientists in many different places using different methods get the same result, then the result becomes reliable. Reality matches the idea again and again. Reproducibility is what separates science from rumor, superstition, and intuition. It's why a fact is a fact, not just one person's opinion. And this connects directly to peer review. Peer review is the process where scientists check each other's work before publishing it. They look for errors, weaknesses, bad data, and incorrect logic. They make sure the experiment was fair, the statistics were done correctly, and the conclusions match the evidence. Peer review isn't perfect, but it's one of the best tools we have for catching mistakes and improving accuracy. It's like the scientific audit system, ensuring quality control before new knowledge becomes part of the scientific record. But here's something just as important: science changes. This is where people sometimes misunderstand. They think that if science updates its conclusions, that means science is unreliable. But updating conclusions is exactly what makes science powerful. New tools allow more precise measurements. New experiments reveal new details. New evidence forces scientists to refine or replace old ideas. That's not chaos, that's progress. Think about maps. Hundreds of years ago, our maps of the world were wildly inaccurate. As explorers and satellites collected better data, the maps improved. We did not accuse cartographers of being inconsistent. We thanked them for making better maps. Science works the same way, constantly improving the map of reality. Now let's discuss something that gets in the way of discovering truth bias, especially confirmation bias. Humans naturally look for information that confirms what they already believe. If you think heavier objects fall faster, you might notice examples that support your belief and ignore ones that contradict it. Science is designed to fight this bias. Experiments are built to challenge ideas, not confirm them. Tools like blind tests and control groups make sure the results are not influenced by what people expect to happen. This is why evidence is more important than authority in science. It doesn't matter who you are: student, professor, expert, or beginner. If you have evidence that challenges an established idea, science listens. Throughout history, many breakthroughs came from people who weren't famous at the time. Science doesn't care about your title, it cares about your data. Now that we've covered the method, let's show how science appears in everyday life. Because this method isn't just for labs or research papers. If you've ever experimented with a recipe, testing different ingredients to see what tastes best, that's the scientific method. If you've tried different ways to fix a device to see what solves the problem, that's the scientific method. If you've tracked your sleep workouts or habits to see what works, that's the scientific method. If you've compared prices or tested which product lasts longer, again, the scientific method. The method isn't foreign. It's the most natural way to learn. Finally, let's talk about what science ultimately gives us, not absolute truth, but increasingly accurate models of reality. Science doesn't claim perfection, it claims improvement. Every new discovery sharpens our understanding. Every test makes our knowledge stronger. Every experiment brings us one step closer to seeing the world clearly. The scientific method isn't a book of answers. It's a toolbox, a way of thinking that helps us navigate uncertainty challenge assumptions and get closer to what's actually true. And the best part is this: anyone can use it. You don't need a lab coat or a degree. You just need curiosity questions and the willingness to test your ideas against reality. That's the scientific method explained simply. The most powerful tool humans have ever created for understanding the universe, and one you can use every day. The scientific method isn't just for laboratories or experts, it's for anyone who wants clearer thinking and better decisions. It's the process that turns curiosity into knowledge questions, into answers, and ideas into evidence. And it's always improving, always refining, always moving us closer to reality. In a world full of noise, the scientific method is a filter that helps you see what's true. If you enjoyed this explanation and want more simple, story-driven breakdowns of how things really work, feel free to subscribe and join us in the next video. Until then, stay curious, because every question is the beginning of a new discovery.